So continuing on our journey in process synchronization and coordination, like we studied, why do we need process? Like what's the main objective of to synchronize our process, right? So we were trying to understand why do we have to synchronize our process, like and what happens if we do not synchronize it. Okay. Um, Now, the critical section problem, right? We begin our consideration of synchronizing by discussing the so-called critical problem, right? So basically, we want to understand. Just let me check if the stream is up and running or not. So let's go to. Yeah. So now, basically, um, let's try to understand the critical section problem. So basically, now we are going to understand. Okay, now we begin our consideration of process synchronization by discussing the so-called critical section problem. The consider a system of n processes. Now each process has a segment of code called a critical section in which the process may be accessing and updating data that is shared with at least one process. The important feature of the system is that when one process is executing its critical section, no other. Okay, so let's have an array of processes. So P0, P1 and up to P of n minus 1. Now what is going to happen is so then we have each of these processes has something called as critical section. So let's try to this has a critical section. Now each process has a segment called, so every process is going to have something called as critical. So even this has a critical section, then even this process has a critical section. Now each process, so basically each process has a segment code or called as a critical section in which the process may be accessing and updating data that is shared with at least, so this is basically, so this code may be shared between different processes, right? Now the feature is basically when one process is executed, so suppose p1 is executing that common area, so p0 cannot access that at the same time. The critical section problem is to design a protocol that the process can use to synchronize. So basically we are trying how to achieve concurrency, right? Or no, let's see what is the critical section. So okay, also basically the goal of critical section is just to allow only one thread. Okay, let's see. Now the way we solve the critical section problem is we need to satisfy three conditions. So okay, what is the problem? The problem is that whenever we are sharing a resource, only one should be able to access. The goal of critical section is only to one thread to execute. Yeah. So basically, Remember, our goal is to achieve. Our goal is to make sure um, only one thread executes the section at a time. Okay. Now, to achieve this, we make sure that whatever our solution needs to follow three principles. So to achieve that, so the three principles that we follow is basically mutual exclusion. This is basically a set based rule, right? So like if a process pi is executing its critical section, the no process mutual exclusion. This is okay. Let's see now. This is, I guess, from set theory, right? Mutual. Okay. Uh, Mutual exclusion is only one thread or process is allowed to. No. Wait, let me see. Yeah. So mutual. Okay. Let's see. Exclusion means like an exclusive access, and mutual is basically so like mutually a contract between them. So what we are going to do is mutual exclusion is only one thread can access the critical section. Only one process is allowed to critical section at a time. So we say only one process is allowed to enter the critical section at a time, thereby providing this mutually exclusive principle. Critical section at a time. And then the second way or the second principle is uh, progress, right? If no process is executing its critical section and some process wishes to enter, then only the process that are not executing in the remainder sections can participate in deciding which will enter this critical section next, and the selection cannot be postponed. So then there is one more criteria. Okay. Now progress. Now if no process executing its critical section and some process which to enter the critical sections, then only those processes that are not executing in their remainder sections can participate. Okay. For example, so I have a P1 that is currently not in the critical section, so not in critical. I have a process P2 that wants to enter the critical. Now if this is going to happen, then only those processes that are not executing in their remainder sections can participate in deciding which is going to wait. So okay, so the sections for code implementing this request is the entry code. No, what is this trying to say? Mm, let's try to understand this thing. Okay, so basically what he's trying to say, if no one is in the critical section, and so there are at least one, so this is P1 and there is P3 as well that wants to enter. This is P1 and P3. Now the system must eventually allow one of them to enter, and the decision must involve only the process that are interested. Oh, so basically while we are making the decision, so we should only consider the P3 and okay, I get what it's trying to say. So if there are processes say P1, P2, P3 and P4, and then P1 is not in critical, right? This is not in critical section. So, and P2 and P3 want to enter. So if P2 and P3 want to enter, then the decision should not, so the decision should be made by only considering P2 and P3. So only consider P2 and P3. Okay. And then third is basically bounded waiting, right? Now there exists a bound or a limit on the number of times that processes are allowed to enter the critical sections after a process has made a request to enter its critical and before the request. So there should be a bound. Then the third rule that we have is basically bounded waiting. So that means if there exists a bound or the limit on the number of times that other processes are allowed to enter the critical sections after a process has made a request to its critical section before that the request is granted. Okay, so there is a bound on which number of times allowed to enter a critical section after the process and made a request. What is this trying to say? Bounded waiting. Let's see. Oh, basically what is trying to say is okay. There shouldn't be any starvation, right? That it is. So I am if there is P1, P2, P3, and P4, and suppose if P2 wants to, so P2 request for critical section access to P1. There is just a bound. Now P1 should not enter in its own critical section. Then P2 will never go that time. There should not be here. So P1 can, if there is a request for P1 critical section, then there should be a limit on it as well. Okay, so to solve the critical section problem, we follow three rules, right? Critical section. So critical section is basically anything when two processes are going to share the resources, we say that is a critical section. So sharing is entering into a critical section. Now we need to make sure that no process is deprived, and then so our goal is basically to make sure that only one process can access critical section, because uh, yeah, because we want to achieve some coordination, right? So if both of them are changing, then again we run into that producer consumer problem, right? So we want to avoid the producer consumer thing. So the way we do is only one should access the process. Now how can be done? First is mutual exclusion, right? That means only one process if p1 is in its critical section, then no other process can enter. But now we also need to make sure that there is no starvation of the processor, right? Everyone should be have the same priority. So third, okay, let's have it as two. We have something called as bounded waiting, right? If I have if I'm having two processes p1 and p2, and then p1 wants to access the common source, right? Sorry, p2 wants to access the critical section. Now p1 cannot go into p1 cannot go into critical section. Like there should be a limit is set. Okay. Third is basically okay. There's one more rule we say, which progress, right? So if I have p1, p2, p3, and p4, right? The p1, p3, and p4. So p2 and p3 want to access the critical section, right? So while considering the priority, which should get what, we only should consider p2 and p3. p4 does not need the critical section, so don't waste anything over here. Okay. Now we assume that each process executing at a non-zero speed. However, we can make no assumptions considering the relative speed at a given point in time. A kernel code may process be active in the operating system. As a result, code implementing an operating system. Okay. Now we make an assumption here, right, that both are going to take at non-zero speed. Okay, let's. Now there is something called as Peterson solution, right? Now next is what we are there is a, because the way modern computers perform basic machine language tasks such as load and store, there is no guarantee that the Peter solution work correctly. However, on the present solution, it provides a good algorithmic description of solving the critical section problem and illustration. Yeah, basically this is what we do, right? So this is nothing but called as Peterson's solution. Okay. Uh, now, okay. Um, Now, wait. Let me see something here. Mm. Yeah, basically we want to achieve. Okay. Mm, just only one process. Okay, we saw the critical section thing, but then let's come back. There's something that we need to discuss here. Mm, mhm. So basically, we need to avoid deadlock as well, right? Okay, so okay, just give me a minute. Yeah, we'll continue with this in the. I'll merge them. Okay, that's all. We'll see. We'll go on. You understand how um uh, okay, yeah, we are basically trying to understand the concurrency issues, right? That is the, so we studied like the solution, right? But then we did not entirely discuss the the synchronization issue, right? First we okay. Let's issues with synchronization. The first is basically, as we said, it's the producer consumer thing. Basically, what is said is the producer should not add to a full buffer. So if there is a buffer, there is no space to add. Producer cannot add to it. Producer shouldn't be able to add to it. Consumer is, if there is empty spaces, then um, consumer should not remove from here. So this is basically adding, and this is removing from an empty buffer. This is the first problem that we happened, right? Now we said, since we will be doing multi-threading, since we are achieving concurrency using multiple cores, the second problem that we have is basically race conditions, right? So why do we have this? Because two processes, uh, process P1, process P2, uh, both are going to be made up of different threads, right? So each process, the smallest, this is P1, this is P2, right? The smallest unit of work is basically a thread. So this is my thread 1, this is thread 2 and thread 3. On similar lines, this is thread 1, thread 2 and thread 3, right? There shouldn't be, now what problem is going to happen is, if so then P1 and P2 are access a critical section. Basically this is a common file, right? Now there shouldn't be so what if thread 2 and thread T are trying to access at the same time? Then which will access is a problem, right? That is nothing but my race around condition. Threads are racing with each other. So we need to so this is basically race condition. Race around is we to remove the to remove the race. The race, this is basically my race condition, right? Who is going to update? The third thing that we have is basically after race condition there is another issue, right? Deadlock. There shouldn't be a deadlock, right? Now what, so there shouldn't be a deadlock. So what do we mean by that is okay. These are two processes and they're going to share the, this is P1 and P2, right? So deadlock should be avoided. So we will see what is going to happen. Deadlock is by meaning is, suppose P1 takes the critical section and does not release it. So this is kept waiting. This will be kept waiting until P1 releases the lock. So we shouldn't be having this as well, right? So all of these three things are overcome in my Peterson solution, right? That basically take care of all of these three things, that is mutual exclusion, progress, and bounded waiting. Now how to achieve each one of them is what we need to understand. Like how will we achieve critical? Okay, so now we said okay, so the solution to critical section is first is basically to do what do you say, mutual exclusion, right? So now how to achieve mutual, our question is how to achieve. So like we are trying to understand how to achieve mutual exclusion. Okay, let's see. There are different ways to achieve okay, Peterson's algorithm. Okay, there are different ways to do so Peterson's algorithm. So no, we define three rules, right? So those are not Peterson's rule. Yeah, this is the first rule, say achieving critical section thing. So mutual exclusion, right? So the first way to do is basically to use a mutex. Now mutex, so mutex ex for exclusion and mu is basically for mutual, right? So basically what we are going to do is, this is a very common and practical thread. So what is going to do is, okay, let's see how mutual exclusion is achieved by mutex. Now this is basically a lock making sure that only one thread can enter the critical section at a time. Okay, so the way so this kind of provides like three different functions for us. So whenever you are going to do this, you are going to have three functions. So first is basically to initialize the thread or to start. So this is mutex, and then this is to initialize the mutex. We are initializing it. The second is basically to lock. We have pthread. So what this does is this puts that lock. The moment a thread enters into a critical section, a lock is made. So thread in critical section, lock is made. Now then what we need to do is, we need, when the work is done, then we need to unlock the mutex. So then we are going to so fourth is basically unlock the mutex. So unlock mutex, basically the mutually exclusive or the mutex is being unlocked here. Then is my fifth, right? The mutex destroy. So what does this do is basically destroys the free the mutex when it has been done. So when used, destroy or perform garbage collection. So basic, is it like a inbuilt lock? The most common and practical way to achieve exclusion in real world programming is using this. So whenever we are going to do multi-threading, we are going to lock and then unlock the resource or the common thing. Oh, I see. Uh, there's a lag, I don't know. Okay, let's refresh. Just yes. Okay, I have to close this page. So let's add on a new page. So let's go to page 2 and then uh, okay, so this is how my so I guess these are okay, let's go back to Twitch. Oh yeah. Mm. Oh, it did start from the beginning. Okay, that's okay. Yeah, so the moment we, so now we are so is this like an inbuilt C function or something? No, no, no. These are library functions from the POSIX threads library itself, and not the system calls. Okay. So the way we do is, if you see, so this is my common thing that is going to be used, right? So the way before I come I lock it, and after I go is I do the unlock. And I'm having three threads, so T1 and T2, right? So before any thread enters, that is how I'm going to do the locking and unlocking. Okay. So basically, first is the practical way to achieve mutual exclusion is through mutex. Now, uh, okay. And now let's see how should we there is one more way to avoid mute. Like there is one more method in which using can do uh, like mutual exclusion. So this is basically using um, semaphores, right? Now let's understand what a semaphore is. A semaphore is basically is a synchronization primitive that is used to control access to a shared resource, coordinate the execution of multiple threads or processes. So it's going to okay. Let's see the working of it. For some reason my PC is stuck. Okay. Yeah. Oh. Okay, let's try to understand how a semaphore is going to work. So semaphore is basically a variable, right? So for example, basically use semaphore is a this is a variable to control access. So it can be either be 0 or it can be a 1, right? For example, a thread T1 enters, then it changes. Okay. Uh, so for example, you have a parking lot, right? So this is my parking lot. And then I have three places. So this is 1, 2, and 3, right? So what I should do is the moment this lot is our so this is 1, 2, 3. Now I should so available I will be having 2, right? The moment get this is full. I should change it from 2 to 1, right? And the moment this is occupied as well, this should become 0. This is basically how parking lots are going to work, right? Uh, okay, did I lose something here? Mm, okay. So basically, it tracks the number of available resources, and then okay, and then it's going to wait and then indicate that there is no available. So now semaphore versus mutex, right? Like what's the best way and what are the differences? So both are used for the same purpose, but then what semaphore is doing is semaphore is to manage a limited pool, uh, like both have different use cases and uh, both are having its own use cases where it should be used and one where it should not be used. Okay, so mutual exclusion value can be 1 or 0, can be binary, thread unlock, critical section. Like ideally both are used for the same purpose. The only thing is both of them have like a special use case where one can be used and the other cannot be used. Okay, yeah, that's all for this video. I'll see you guys in the next one. And then we'll try to understand the remaining two principles and then we'll sum everything up. So that's all for this lecture. Hope you guys liked it. See you guys in the next one. Till that time, take care. Bye bye.